Good morning. Hello. It's so good to be back, right? Post-COVID, do we say post-COVID? But we've looked forward to this event for so long. Good morning. I'm Meredith Land. In addition to my usual title as news anchor for NBC5, I am also chairman of the National Advisory Board of the Laura W. Bush Institute for Women's Health. And it is my pleasure, honored. It's my pleasure to serve with my dear friend, Lana Andrews, who unfortunately could not be here with us today. We are so happy to welcome you to the 7th annual Laura W. Bush Institute for Women's Health Coffee and Conversation. Each year we bring you interesting information that can make a difference in your life or somebody's life that you love. The presentation this morning, several of them, are so relevant to every man and every woman in this room today. We are grateful for the underwriting for today's Coffee and Conversation. It has been provided by our Dallas-Fort Worth National Advisory Board members. Please stand and be recognized for all you do for the Institute. Thank you. Many of you are unfamiliar with the Institute, so we will share a brief video to get you up to speed.
I didn't know. I thought all medical procedures and diagnoses were the same. Now, because of the Laura Bush Institute, I know there are differences between men and women, and I can insist on personalized care from my healthcare providers.
Because diagnostic standards have historically been based on the male physiology, women, you and the people that you care about are at greater risk. This is what the Laura W. Bush Institute for Women's Health is passionate about. If your physician is well informed, you could avoid a misdiagnosis, complications, or even a delay in life-saving treatment.
Gender bias in medicine just about killed me. When I was 40, I knew I was having a heart attack with chest pains, shortness of breath, and sweating. So I went to the ER. Over the next 4 hours, I was misdiagnosed twice, even with a blood test confirmation. It took 3 days, but even then they weren't prepared for that. So I had to come back the next day for a stent. Sex and gender differences matter.
The Laura Bush Institute is integrating sex and gender differences into healthcare curricula so future physicians and nurses get the latest information and women receive the personalized care that they deserve. We host events in communities across Texas sharing vital health information with women and girls to improve their lives mentally, physically, and emotionally. We provide fun, educational programs that inspire self-confidence and personal power in young girls. We also entertain college women with events that teach self-defense, acceptance, and friendship as they navigate their college years. Our signature events across Texas bring fascinating people who inspire us and lend support to our mission and programs. Through our focus on mental health, we provide transcranial magnetic stimulation treatments for women with chronic depression and anxiety.
I no longer live with the crippling depression that I did before deciding to try Brainsway Deep TMS. Thanks to Brainsway TMS and the staff at Texas Tech University, and of course God, I sit here today with tears of joy streaming down my face as I believe I've been given a second chance of living life.
We also facilitate breast and cervical cancer screenings for uninsured women.
If it would not have been for the Laura Bush Foundation, I know for a fact that I would not have gone to get checked out, and I never would have found out that I had early stage cancer. I am cancer-free.
Your support plays a critical role. Join us. Together, we can improve the lives and health of women everywhere. Our thanks to former First Lady Mrs. Laura Bush, our National Advisory Board, our community boards and volunteers, and the Texas Tech University Health Sciences Center.
It is now my honor to welcome the former First Lady of the United States, Mrs. Laura Bush.
Thank you, Meredith. Thank you for your leadership, Meredith, as co-chair of the National Advisory Board, and thanks for your friendship. It sure is nice to have the landline on the Laura Bush Institute team. You may not know it, but Meredith is on our television news every day. A heartfelt thanks to Lana Andrews, our other National Advisory Board co-chair, and to all the National Advisory Board members who have joined us today. Thanks to Connie Tyne, the Executive Director of the Laura Bush Institute for Women's Health. Thanks to your terrific work. And the Laura W. Bush Institute has earned the respect from medical institutions around the country for its groundbreaking discoveries in gender-based medicine. And that makes me very, very happy, and thanks to Connie also for that. Women and girls everywhere are benefiting from this research, and I'm proud to be the namesake of such an esteemed health institute. Of course, I want to thank everyone here today. Thank you for your support for the Laura Bush Institute for Women's Health. We're happy to host you here at Old Parkland. You may not know, but George and I have an office just a stone's throw away. We work in the newest building on the Old Parkland campus. It's called Freedom Place, and we have wonderful views of Dallas from our beautiful offices. I thought you might be interested in knowing a little about this campus. Our friend Harlan Crow developed Old Parkland. He renovated the original 1913 Old Parkland Hospital building for his office space, which is right next to us here on Old Main. He designed the historic 1922 nurses' dormitory into now what is now called the nurses' quarters, but it's featuring offices, a tavern, which the nurses might have liked, and an exquisite ballroom. Though they don't look it, the rest of the buildings that you see around here are new. With the goal of inspiring camaraderie among colleagues and collaboration among businesses, Harlan developed Old Parkland with a theme. He calls it an American experiment based on the founding of our country. Even though it looks like sunlight coming through the window above, we're sitting underground here in the debate chamber, better known as the bloodline of Harlan's American experiment. Designed to foster debate and open dialogue, this space is filled with style elements from ancient Greece and Rome. Harlan selected these ancient cultures because of the influence they had on our founding fathers, who are the heart and foundation of his American experiment, which is displayed in this building right above us. On the front of this podium, you'll see an owl symbolizing wisdom. Woven through its talons is a ribbon engraved in Latin with the virtues fortitude, justice, temperance, and prudence, the four cardinal virtues for a fair and balanced life. And on the sides of this room, we see the statues of prudence, and fortitude. And I hear the statues of temperance and justice are on the way. So if you can't tell, this is a unique and special place, and I'm glad that we've gathered here today for our unique and special program. For several years, the Laura Bush Institute for Women's Health has invited dynamic speakers to present fascinating topics in communities around Texas. Today, we're fortunate to hear from Dr. Teresa Baker and Dr. Timothy Chan. They'll discuss the groundbreaking research that's been done on cancer vaccines, as well as the tangible hope this offers for millions of men and women around the world. So thank you to Dr. Baker and Dr. Chan. Thank you for joining us today, and thanks especially for your impressive and important work. So now I'll turn back to Meredith to introduce today's program. Thanks, everybody, for coming today.
Thank you, Mrs. Bush. I would like to mention that the Laura W. Bush Institute for Women's Health is a nonprofit. It's a 501c3 organization that welcomes the support of people like you who really want to make a difference in the lives of women and promote that personalized care and medicine for everyone. We want to thank our Dallas donors that are here today, and of course our National Advisory Board. We are able to bring you this important program today, all because of you. Now we want to begin our program. I would like to introduce Dr. Lance McMahon, Senior Vice President for Research and Innovations at Texas Tech University Health Sciences Center. His personal research in behavioral neuroscience and addiction has led to extensive NIH funding throughout his career. Dr. McMahon will introduce our speakers and moderate a panel the last 20 minutes to address your questions. Welcome.
Well, I can first say, wow, this is an incredible setting, and I'm very happy to be here. Thank you, Meredith. Thank you, former First Lady. And I also want to acknowledge the leadership of our president of the Texas Tech University Health Sciences Center, Dr. Lori Rice Spearman, who's to my right. It's a pleasure to be with you, and I'm very excited about the program we have today, entitled What the Emerging Science of Cancer Vaccines Will Mean to You. We're going to begin with an update on a very important cancer vaccine that was approved in 2006 and provides a great model for future vaccines. We have invited Dr. Teresa Baker to explain this current example of cancer prevention and share its effectiveness. Dr. Baker is board certified by the American Board of Obstetrics and Gynecology and is a fellow of the American College of Obstetricians and Gynecologists. She combines her private practice with academic medicine as chairman of the Department of OB/GYN at the Texas Tech University Health Sciences Center on our Amarillo campus. Dr. Baker holds the Rush Endowed Chair in Women's Health and Oncology and is director of the residency program. We also thank her for her leadership in women's health, and I would like to invite Dr. Baker to the podium.
Thank you, and thank you all for coming. I get the good part of this talk. I get to tell you about a real success story in medicine, and that's not what we've heard as of late much. But this is a novel concept, and it led to a Nobel Prize. And what the concept was can a viral infection lead to the development of cancer? So what you have to understand about our bodies and our cells is that they are managed by DNA inside the cell. So the cell system, what the original idea was this thing called the two-hit hypothesis. So every cell basically has two alleles that drive that cell, that tell that cell what to do. And what the two-hit hypothesis is that let's say one of those cells, one of those alleles on that cell is damaged. Maybe it was made a little wrong, maybe it was damaged in some way. Our bodies are so incredible that our systems, our immune systems, can probably clean that cell up, get it out of there, program cell death, or even repair that allele. But the two-hit hypothesis says, what if a second hit happens? What if you go into the environment and maybe you smoke a cigarette? Or you are introduced to a virus. When both alleles have been damaged, now we lose control of that cell, and that cell becomes cancer. That's kind of how this whole story began. The second part of the story is the discovery of a virus called human papillomavirus. And this gentleman changed the world. In 1973, he was given the Nobel Prize for his work on cervical cancer. And what he proved was that the HPV virus infects women's cells and that those infected cells become cervical cancer. And that was when the story began to change. We began to, Dr. Chan's going to talk about other viruses that we know can do this now. But this was the novel work that started this. What we know is that not every person that's infected with HPV will get cancer. It's a very small group. And then of those HPVs, just like coronavirus, I promised I wouldn't say that today, I'm sorry. But just like coronavirus, it has continued to mutate. Now we know there's over about 90 different viral strains of HPV, but only a subset of those are dangerous and lead to cancer. So then two things began to happen. One was that we realized it wasn't just cervical cancer. So this is the burden of the disease. It's urogenital cancers, and it's now the leading cause of head and neck cancer in men. So what we're learning is that HPV isn't just a women's disease. It's all of our responsibility. And at the same time, the development of the Gardasil vaccine, or the HPV vaccine, started. Now, this vaccine has evolved over time. We're now in its third iteration. It now involves 9 different viral strains, and those 9 are the most virulent, the most cancer-producing, so that we have continued to see this story change a lot. And here's the beauty of it. You can see that if we use the vaccine, you see those cancer rates fall dramatically. But this isn't new news. We've known this for a long time. So the question is, why are we still at about a 30% vaccination rate? And this is where the talk gets a little uncomfortable sometimes. But here's what we know. HPV can be sexually transmitted. That's possible. It can also be transmitted by close contact or touch. It can also be transmitted from mother to child. So the person that is infected with HPV may have had nothing to do with their own exposure. And that connotation that we were vaccinating young women against sexually transmitted diseases was a hard message. And I understand that. I really do. I've got 4 small children myself. And, you know, our target age for this vaccine is 9 to 26. But we really try to get it at the 12-year-old age. And to think about my child having sex when she's 12 makes me want to throw up. But it's probably going to happen in her lifetime. And the analogy I like to use with parent groups is the bike helmet. You know, you don't put the bike helmet on your child when they're driving down the highway on their bike. You don't put it on them after the crash happens. The idea is to put the helmet on when they're in your driveway, and you can talk about risks and benefits. And unfortunately, we have to start those conversations earlier with our children. So if we could get away from thinking about it as a sexually transmitted virus and just think about this as a cancer-preventing vaccine, I think that's where this conversation should go. I think all of us as parents would swim through fire for our kids. So just if you'll let go of some of it and rethink this as maybe the one way that we can protect our kids from cancer and have those conversations that need to happen. We've now expanded the age range of the vaccine to 45, and that's another interesting conversation. But the truth is we're living longer, we're active longer, and life is unpredictable. And the fact that you may be co-infected with another HPV later in your life may put you more at risk. So the vaccine's out there, it's available, it's one of our best success stories. I'll be here all morning. I'd love to talk to any of you about it, but I think now it's time to hear about the novel ideas that are coming.
Thank you, Dr. Baker. As a husband of a wife who's also a family practice physician and who has 3 children, I can tell you I'm very impressed. 4 children, and with all of your credentials, that's pretty amazing, And this is a very difficult conversation. I think we can all acknowledge that. And we have a little bit of vaccine fatigue, I think it's pretty safe to say, over the last 18 to 24 months. However, these are important conversations, and thank you all for engaging. And thank you, Dr. Baker, for helping us to sort of change our perspective on how to approach the cancer vaccine, not so much as a sexually transmitted related thing, but just a overall cancer prevention approach. Now, let's address the present and future of cancer vaccines from the perspective of one of the country's foremost researchers, Dr. Timothy Chan. Dr. Chan is co-director of the National Center for Regenerative Medicine at the Cleveland Clinic. He is co-leader of the Immune Oncology Program at Case Comprehensive Cancer Center. Dr. Chan is a physician, he's a scientist and a professor. All of those things are impressive enough on their own individually, but when you put them all together in a single person, it's quite an accomplishment to be a successful physician scientist. His cancer genetics lab and patient practice focus on immunotherapy research with the goal of developing cancer vaccines. He has a CV this thick. We won't go through it now, and I'll just ask Dr. Chan to come to the stage to provide his remarks.
Thank you so much, Lance, for that kind kind intro, and I just want to say thank you for the amazing opportunity to come here and join you at this wonderful venue and at this wonderful event. Thanks very much to Connie, to Mrs. Bush, to Lori, to Meredith, and the Texas Tech team, as well as the Laura Bush Institute. I am just amazed at the amount of work and the amount of good that this institute has done over the years. And so when Connie actually, contacted me and said, hey, do you want to give this talk on cancer vaccines? Well, I work on cancer vaccines, so my inclination was yes. But more importantly, I thought, wow, we're coming out of a pandemic, all this stuff going on in the world. What an awesome opportunity to talk about something that gives some hope. Right? That will leave you at the end of the day with perhaps what I wake up with every morning, which is a wonderful opportunity to try to make a difference and make people feel better when they're down and out. Right? So I'm going to hopefully take you through the journey of cancer vaccines. Right? This is a field that is absolutely exploding now. When I first went into oncology, for instance, melanoma patients, if they're disseminated, this was a death sentence. Response rates are 1%, if that, with highly toxic therapies. Nowadays, with immunotherapies, which I will take you through the development of, we see that the response rates are greater than 50%. And it was just published that the 5-year survival tops 50%. When I was at Memorial Sloan Kettering in New York, we just ran a trial, a phase 1 trial, where combination immunotherapies have now resulted in kidney cancer response rates of greater than 90%, whereas previously this was 1%. We live in a time, I want to impress upon you that we live in a time where these medical breakthroughs are happening, some of which are in the media, some of which are not, but I wanted to make sure you knew that these advances don't come around but once every 1 or 2 generations, and we're living through that. And so I'm going to try to put what I'm going to talk about into context. Hopefully this can help folks that you may know to receive some of this information, as well as the Institute for helping spread the education. So vaccines. Right, so what are vaccines? Vaccines generally are a relatively easy way to reprogram your immune system, right? And this concept has been around for over 100 years. In terms of cancer vaccines, and I don't have a pointer, so I'm going to go ahead and just say left and right on the slide. On the left side, you see this gentleman in the 1800s, William Cooley. This was a physician that was a prominent physician at the time, at the turn of the century of the 1800s, who thought, okay, can I treat cancers with infections? And what William Cooley did was actually he injected sarcomas, these tumors of the soft tissue and muscle, with bacteria. And it was pretty crude at the time, and but amazingly enough, some folks actually responded. And he treated the daughter of one of the original Rockefellers, and her tumor shrunk. And now there were problems. Not everybody responded, and if you just put bacteria, then there are other issues. But the concept was actually demonstrated that the immune system and cancer talk in the same language. Okay, and that the immune system can be used to fight tumor cells and cancers. And now you fast forward more than 100 years later, you see that in 2013, with the advent of some new agents that are on the scene now that are available to everybody, like the different immunotherapies, immune checkpoint blockades, anti-PD-1, if you may have heard about this, that made the breakthrough of the year for cancer for cancer immunotherapy in Science magazine. And since then, this has spawned a Nobel Prize and multiple past Nobel Prizes formulating the basis of all of this. And so what does this involve? Well, the immune system is designed through evolution to help us get rid of what is not supposed to be there, okay? So it fights what I call non-self. If you get a cut, for instance, if you undergo surgery, if you have a wound, it is It is the army of cells in your body that allows you to fight off infection and disease. But what a lot of people don't know, and honestly, only in the last 10 years have we really understood this fact, that it is also responsible for fighting non-self that comes from inside. If you smoke, it can cause mutations. If you have HPV, it can screw up the cells in the cervix and head and neck. And these become, in essence, partly foreign. They're not supposed to be there. And it turns out that the immune system has evolved over many eons to actually allow us to fight some of these things as well. And so this is what I put here. And some of these slides, I'm going to try to take you through the journey of all this and talk about a little bit about the science, but give you a little bit of grounding in the basis of vaccines. So again, on the left, if you get a cut, bacteria can come in, and it's very important for us to fight this off, right? So the immune system has evolved all these soldier cells to try to destroy these bacteria. Now, on the right side, you see that the threat doesn't necessarily come from outside all the time. It can come from inside, because our cells, we have billions and billions of cells, okay? And they are all dividing all the time. Dr. Baker actually mentioned very presciently that all our cells are dividing all the time, and viruses can screw them up. Too much sunbathing, for instance, can cause mutations. And these things can cause changes that make the cells more non-self. And so the immune system actually can fight off and help you prevent cancer. So it is very important to have a healthy immune system as a cancer preventative. It really is something that we have realized in the last several decades. And so the details are not important. This is just simply up here to show you that there are a bunch of different cells. In the media, we may talk about T cells, whether your T cells go up, or antibodies. There's a component of the immune system there that acts really quickly on the left. And there's a slow response immunity that kicks in once you get something like vaccines. That's where antibodies fit in, right? Like you hear in the media about antibodies and so forth, boosting the fight against COVID and other viruses. So it's a bunch of soldiers. It's very complex and it's running around it. But I want you to pay attention to things called the B cells and the T cells up here. Those are the primary general soldier cells that are out there that love to coordinate your response. You have to educate those B cells and T cells to fight off, to teach them what to fight off, right? And for cancer, these are not the typical bacteria that we see, right? Over the last 10,000, 20,000 years, the bacteria that we as human beings see in our environment, we've essentially figured out ways to fight these things off. But the cells that are in your body that arise, these are much harder. They're much more similar to self, okay, your own cells. They're slightly different. So it makes the immune system and these soldiers work much harder. And so sometimes you need to train these cells in order to fight off cancers or self cells more efficiently. So it turns out that the immune system is a wonderful way to do this, right? The immune system, now the terminology here is not important, but simply to say that it's a perfect cancer agent. The immune cells are designed to get rid of non-self, right? And what I list up there, T cells and antibodies with diversity, this is simply to just say that these T cells and B cells can generate many different modes of attack, right? These are all essentially drugs. We sort of, in the healthcare industry, celebrate if we make one vaccine and say, oh, that's fantastic. In any time in your body, you have 10 to the 18 different types of cells that are floating around that can help you fight off whatever. Right, so it is quite an amazing sort of system that we have, that we've been granted. And the timeline of immunotherapy, starting from William Cooley that I mentioned, it started years and years ago, over 100 years ago. And over time, there has been development both on the infectious disease setting as well as in the cancer setting. And over the 50s, 60s, 70s, knowledge has increasingly been gained over this time. And I think the main time period in which this thing really was hit out of the ballpark was in 2011, when the first immunotherapy was developed. And these types of immunotherapies allowed us, and they're antibodies actually, and they allowed us to be able to reawaken our immune cells and to fight off cancer cells. And for the first time, this drug is called IPI in 2011. For the first time, we were able actually to really systematically activate the immune system against cancer. And this led to a Nobel Prize, and subsequently, very shortly afterwards, a drug called anti-PD-1 was developed, right? Now, these drugs also awaken the T cells. They activate the T cells and essentially take the blinders off and allow the T cells to go kill cancer cells. And you have seen some amazing results. Jimmy Carter, for instance, had a complete response. He was on, he was going to die. Okay, he had metastatic disease, complete response, essentially years and years free of disease now. And in my own clinic, I've had folks over 20 years that are out of therapy that have just done fine. Now, not everybody responds. This is a great baseline of development, for therapeutics for patients, but less than 50% of patients really benefit. And some diseases, patients with some diseases do much better than others. And so one of the things that I'll impress upon you is that in cancer therapy, there are two types of approaches. One type on the left really is where it's very complex, and it's meant to be, where folks will make a drug and try to target one specific protein amongst thousands and thousands of proteins. The immune system is much more elegant. The immune systems are these cells, as I put up there, that have developed over eons actually to help destroy non-self. Okay, that is what it does. More than that, it has memory, which means that you can train these soldiers that I talked about to really destroy things and keep destroying what's not supposed to be there for the lifetime of the patient, which is an amazing thing, because after a while, if you give a drug, people can become resistant, much like antibiotics for bacteria. So this is an example here of how this has impacted our field. All right, so on the left, you see the results of a patient of ours when I was in New York at the Memorial Sloan Kettering Cancer Center, and my colleague Paul Chapman, who's a melanoma doc, saw this patient who had metastatic melanoma. I mean, you see the scan there, and you see that lump there on the chest, which what she had. She was in trouble. You remember, this thing did not respond to anything more than about 1% to 2%. She was given a single injection of ipi/nivo, and the entire disease disappeared, which demonstrates the power of the immune system. And on the right, what you see here is the general response rates. The graph is a little complex, but what we can probably appreciate is that across different cancers, patients get benefit, and as a single agent, the response rates roughly are around 20 to 30%. Not great, right? However, compared to the 1% or 0% previous to this was a game changer. And for patients that actually do respond, you see what can happen on the left, where you get these durable responses where you train the immune system to forever recognize those cancers and eradicate them, which is really what we're trying to do. So this is a little bit of a complex slide, but it's basically here to show you that there are a lot of things on the tumor cell side and on the immune cell side which actually need to happen. And these need to join in the middle, which is shown by the green box. And I want to introduce the concept of the epitope. Okay, the epitope is basically what a vaccine does. It is the spike protein epitope and others if you've heard about. These things are the things that are in vaccines that train the immune system and T cells to help you fight off not only infectious diseases like HPV, but also cancers. And so you need that middle box actually to come together, and you need that orange dot to be correct. You need the right epitope or the right signal that allows the tumor cells to be seen. Okay, you can imagine it as your ID card. So some of our original work, which started over a decade ago, basically showed, and this is a little bit complex, but showed the concept that when a tumor cell has a lot of mutations, when it builds up all this damage from smoking or from UV light, these are the types of tumors that immunotherapies in general are most likely able to cure, right? Because the more differences a tumor has, as shown up there on the top panel, the more likely it is for the immune system to be able to find one of those epitopes, you remember those orange dots, to kill that cell. So this was a fundamental concept that was underlied a lot of the development of new cancer vaccines these days. And so what are these things? Well, these antigens or epitopes, they're called neoantigens, but what they are can be any protein in the body, right? They can be any protein, and when a protein undergoes a mutation, which happens in cancer, so cancers develop when you get mutations, what happens is that some of those proteins aren't supposed to be there. And so what happens is the immune system gets very angry. They recognize this as being foreign. Remember the concept of non-self, and it programs T cells to go ahead and attack, all right? And so the T cells go ahead and attack, and you get a rejection of the tumor cell. That's the whole concept of how vaccines work, including the HPV vaccine, including some of the new ones, which I'll tell you that have developed, that have generated some striking results. So how does this happen? Well, you get the shot, okay, and you get the right epitope there. It goes into the immune system, and remember what I said before, it shows the T cells and other types of immune cells what the right epitopes are. It identifies, it places the right ID on the right cell, which allows the T cell to then go kill that cell. That's how almost all vaccines work. Okay, and in the setting of cancer, that is what is needed to help the immune cell kill the cancer cell, which again shouldn't be there. So what are the types of cancer vaccines? Well, there's preventative vaccines, which Dr. Baker talked about. These are Silverix, Gardasil, and others, which help you prevent a cancer that can develop years later from a virus or from something that develops. And I'm going to go through some of those viruses that are approved and ones that are coming online. And then there's also therapeutic vaccines. And that is, these are vaccines which, when you have a tumor already or a disease, you already have an illness, they can be therapeutic. They reprogram the immune system to kill whatever type of tumor cells you have, including melanomas and others. And so these are some of the viruses that cause cancer. I'm going to run through these very quickly. Dr. Baker talked about human papillomavirus, of course. You know, it is just and she showed this already, but it is literally the #1 cause of head and neck cancer now, right? Which is amazing because not so long ago, smoking was. Now smoking is no longer, the cause. Not only that, the rates are going up. So this affects everybody, both men and women. But there are other cancers as well where a preventative cancer vaccine can be important. Epstein-Barr virus for lymphomas and nasopharyngeal cancers. And recently, interestingly enough, Epstein-Barr virus has been linked to multiple sclerosis. Okay, so it turns out that long-term infection with EBV scrambles the signal of the immune system and eventually causes multiple sclerosis. How devastating is multiple sclerosis, right? So it's not just cancer, but it's a variety of other diseases that are caused by these viruses. And of course, many of you know about hepatitis B and C. These things, we as healthcare workers, we are required to get the hepatitis B vaccine, right? Because we're at increased risks. These things can cause liver cancers. And also things that are associated with AIDS, like human herpes virus 8, and also there's a rare skin cancer called Merkel cell disease, and MCV is the cause of this cancer. And so there's a lot that we're learning. It's important to understand that our environment is actually potentially increasing our risk for different cancers, and there will be more of these that are found over time. So this is simply just to reiterate what Dr. Baker had mentioned, that HPV has been a game changer, right? This is published from the New England Journal, and those lines are basically showing you the cumulative incidence of cervical cancer. And you can look at the green line up there, what happens when a population of patients are vaccinated successfully at 17 years or under. You actually eliminate this disease. This is the power that can happen, and why education is so important now, and some of the work by this institute is pushing forward, right? Because the challenges now are not simply that the technology doesn't exist. It does. It's around. It's been around for half a decade. It is really education on how one can think about these and make this more accessible and tackle disparities, right? Which is it's a big issue now. I'm going to talk a little bit about one of my patients here. Why are cancer vaccines important? Well, so this was very interesting. This was a 16-year-old girl with a skull-based tumor in our clinic, and she had a very aggressive head and neck cancer, and she was going to die. She had failed chemotherapy and so forth. And as a last-ditch effort, we went ahead and sequenced her tumor, and we found 12 mutations, and we found one of those successful orange epitopes, okay? And we went ahead and put her on anti-PD-1, and she had a complete response. And she was able to go to college, able to go to graduate school afterwards, and was able to maintain a cancer-free condition. And what you see on the top is her PET scan with some of her lesions disappearing. And we found that it was largely due. Now, the question is, okay, well, this doesn't happen in everybody, right? I wish everybody had these types of responses. So we scienced the heck out of this, all right? And we figured out that basically there was one of those epitopes that was responsible, that one in the red. And we scanned all the potential epitopes that could potentially be reactive to, and it turned out that anti-PD-1, which is really, as I said before, awakens T cells. It awakens many of the T cells, right? Turns out that one of them was responsible for causing her tumor to completely disappear, which is the one in the red. And it turns out that this has remained in her system all this time. Wouldn't it be wonderful if we could harness the ability to detect and use those types of epitopes for broad vaccines? That is the concept of cancer vaccine development, right? So I hope you understand that it is the ability to diagnose the tumor properly, to use a bunch of science and genomic sequencing to figure out exactly what is wrong, and to direct T cells to be able to fight off those specific ID cards. Okay, that is what it's all about, right? And it is only possible because of the amazing advances in sequencing and basic sciences and clinical sciences that we all, as a society, has elected to invest in, right? In fact, one of the things I will say is, I know it's not supposed to talk about COVID, but I'm going to just mention this one time. And that is the reason why these vaccines and monoclonals have been able to be put out so quickly was that prior to the development of these vaccines by BioNTech and others, all of these platforms were anti-cancer vaccines. COVID was not on the map. The reason why RNA and all these things were being developed was because phase 1 trials were already using them. We ran many of those trials ourselves. And so they were able to just swap out those little red bars, those cancer epitopes, and throw in the spike. That's why it was so fast. Without all this other basic research, we would be in a much, much worse position right now. And it is a testament to the fact that sometimes science and something beneficial to society may come from a completely different direction. And we have very hard time to actually predict. That's why I'm a big proponent, even though I'm a clinical scientist, of funding for basic science. And that is a huge, huge, huge thing endeavor. So as a Nobel Prize winner from Japan once said, we don't know what mountains we will need to climb tomorrow. Okay? So how does this work? This slide basically shows, as I said, is that when we get a patient gets a tumor, we sequence the tumor, and then we identify which of the little epitopes are important, and then we use those to develop a vaccine and give it back to the patient. All right, so that is the paradigm. And this is complex, but I just wanted to impress upon you what is involved, and that is a cancer patient will undergo sequencing. There's amazing genetics now. We can sequence the entire genome in one day now for about $1,000. And this has come down from the 90s. Actually, a lot of this started in the Bush presidency, actually, for the whole genome sequencing, right? And the first genomes cost a lot of money. It was $500,000, took months and months. In our lifetimes, we have seen this now become a desktop assay. I have my own lab, a little box that can sequence your genome in a day, which is, to me, just mind-blowing, right? So this is what's being used, and the data is used to identify those epitopes, and those epitopes are used to actually develop vaccines. And so what are the platforms? Now, I put this up there just because there's a lot of information, on the media and so forth, RNA, virus vectors, AstraZeneca. What's the difference between all of this, right? All of these things. Well, RNA is a molecule which has been on the news. It's highly successful, and it is what encodes all the proteins. It's what tells the body what to make, right? So you can use RNA as a vaccine, and it's easier and it's faster to actually change the sequence and make. The classic ones, like the original polio vaccine, the flu vaccine, for instance, are peptides and proteins. Those are the classic ways to make ones. And it's harder to make those because imagine you have to grow up big vats of virus in order to make the vaccine. You can do an intermediate, which is a viral vector. You take like a harmless cold virus, you stuff in a peptide that you want your T cells to fight off, and then you can actually use that as a vaccine. So some of the original, polio vaccines, a Salk vaccine, the Ebola vaccine, for instance, actually makes use of that technology as well. So these are some of the next generation ones, right? So I promised to show, some of the ones that are on the horizon. This gets more and more advanced, and you may want to know about these two things. There are next generation adenovirus vectors, which are already currently being used in some of the different viral vectors, and there's something called self-amplifying RNA, where you can design these things to be a tiny bit of material you inject. You don't need all these big production processes. You don't need the freezers to freeze down, things down to -80. With self-amplifying RNAs, which are now exploding on the scene, you can take these to third world countries, Africa. They can be at room temperature, lyophilized into a powder and be given. So this is what is coming next. And as you know, I think one of the things that the pandemic has taught us, that we can never take these things for granted, right? We live in a world where we are part of our environment, and we need to prepare ourselves, as I was talking about at dinner, for a potential next wave. I think we are much more prepared now, but with some of these different delivery vehicles, I think we'll be even more prepared. Some of us, including myself, we're in efforts now to make pan-coronavirus vaccines, which would target 20 different places throughout the entire family to just basically boost immunity across all the viruses to make this just basically not a problem anymore. So I think that's where the field is headed. A lot of this technology is going to be re-engineered for cancer, of course. I'm going to go ahead and skip this. So these are some of the next generation approaches. You can use things like RNA, and you can use them in combination with self-amplifying RNAs together. When you use two different things together, they can drive up the immune response even more. I'm going to show you how this can work. So we're running phase 1s, and I want to take a little bit of time to mention that despite the pandemic, it is very, very important to note that other diseases like cardiovascular disease and cancer do not stop. Okay, We at the Cleveland Clinic, unfortunately, live in an area where there's a lot of, the smoking rates are still very high, and folks have come in with large tumors that are essentially uncurable. So, if you have friends out there to tell you, it's important to tell them that cancer screenings are still very important. These are critical, all right? But I mention this because these are phase ones that were done prior to COVID, and the cancer trial efforts stopped, rightly so, because we shifted towards COVID to get rid of that problem, and then we shifted back again recently. And what you'll see in the next 5 to 10 years, I think, is a massive doubling down on this. This is one of the first patients treated on our combination next generation platform. It's a little bit complex, but what you see here is you see one row being where this patient had metastatic lung cancer, week 8, week 16, and week 48. All right, and what you see in the blue arrow is that this woman's tumor has just disappeared. All right, so we sequenced the tumor DNA, we identified the epitopes, made it into a vaccine, and it just basically eradicated the tumor. This is another example. This patient had a large liver lesion from, I believe, a colon cancer. The most important part is actually at the bottom. You see a PET scan there. You see that area that's lit up? That's in the liver. That's the tumor. Big tumor, right? This thing covers essentially half the body. After some of our initial trial results and a personalized vaccine, you see that this thing has disappeared and she remains disease-free. So not everybody responds as well, but what we're seeing is some very, very powerful effects that are harnessed by the immune system. And this is simply up there just to show you that all those T cells, all those soldiers, previously they did not react against the cancer. Afterwards, you see that they all went up, right? They all reacted against the tumor. And you see that patients, these are survival curves, that the patients that saw that blood markers for these cancers decrease after the vaccines lived a lot longer, right? And so these data now are in early phase ones, of course. It turns out that much of this progress happened literally months before COVID hit, but I think we are, as the pandemic is dying down, we're now sort of getting back to the mission, and hopefully this will continue through clinical trials. So I'm going to stop very soon here. The near horizons, right? So right now I just wanted to leave you with the understanding that these types of advancements will not happen, may not happen for another generation. And it is incredibly exciting and an honor for somebody like me to just wander in. When I went into oncology, melanoma, renal cell carcinoma, these were death sentences, right? And it is just amazing how much response is happening now. And in fact, if there is any silver lining from the pandemic, it is in times of need, we come together and we rapidly advance the science to meet the challenges. And that is something that our country, as well as many others throughout the world, are able to do. And it is just an amazing time because a lot of this is going to get repurposed into our mission for women's health and cancer. A genome can be sequenced in 1 to 2 days, vaccines produced in weeks. The personalized cancer vaccines that I've showed you were produced in a week and a half, okay, so very quick. Tremendous potential for patient society in our country. And acknowledgements, this is my research group here. This was an event at the Cleveland Zoo. So if you're ever up there from Dallas, it's a wonderful opportunity. It was the Asian Lantern Festival. I thought, wow, this would be interesting. Asian Lantern Festival in Cleveland. Okay, so let's go ahead and check it out. Why not? Well, let's invite everybody over. We had a break from the masks at the time because it was outside. Got to see all the animals and everything, but it was a wonderful event. And of course, thank you for your engagement and support. We are all in this together. I want to point out that while the government and NIH does a wonderful job, it is the grassroots and community engagement that really drives the education, the access, and the excitement. This is a story that I will say is that the very first human genome was sequenced with philanthropic dollars. Okay, so a lot of people don't know that, and it is a fact. And the very first immunotherapies were developed just because somebody had an idea, and look how much better we are for it. So thank you very much for your attention, and it's wonderful to be here.
That was incredible. I'm a geeky scientist, and I study the brain. I don't study the immune system, and even I could understand at a very basic level, fundamental level, the information that you presented, Dr. Chan. So thank you very much. So we're going to now have, 15, 20 minutes of question and answer, and I know that we have a lot of very engaged, intelligent people in the room, so we look forward to questions from the audience. I will say that we've been encouraged. Many of us have personal stories, very personal stories related to cancer, and if you have something that you'd like to share with one of the speakers, I would ask you to come up afterwards and maybe talk with them personally about any kinds of personal stories that you might have. In the meantime, I think there's lots of general information that we can share with one another, with Drs. Baker and Chan. One of the first things that I would ask is, this is amazing. It seems to me to put this into practice, there's so many different issues that we have to solve moving forward. You're talking about sequencing tumors, we're talking about personalized medicine. All of us would like to have this widely available for every one of us or loved ones who might have cancers. I guess I'd ask Dr. Chan and maybe Dr. Baker to think about offering some ideas related to making this a widely deployed sort of approach, because you have to get people to come into the clinic. They have to be willing to be monitored. You just reminded me today I've got to get my colonoscopy. I'm 52, and I skipped that first 2 years. And so you have these are tough things. People have to come into the clinic. They've got to be able to engage in the process. There has to be the technology available. And so you talked about the government, Dr. Chan, and certainly to make these kinds of things widely available to the public, private industry has to get involved. So I guess just talking about some of the more general concepts associated with making this a more widely available technology that all of us can benefit from.
No, Lance, that's a great question. And there are two parts to that question. The first is the diagnosis part and then the therapy part, right? The diagnosis part is that these days, for at least cancers, women's cancers, and general cancers, the genomics is an integral part of the diagnosis. And, sequencing is now approved if you have advanced disease, or should be approved, and your insurances should cover this, because there are cross-cancer approvals that are now certified by the FDA. The issue is one of accessibility and practice, right? In actuality, as we know, the healthcare industry is like a big tanker, and it's really slow to steer, and you have to do a lot to push things off. I think compared to when we started, in earnest for precision oncology, it's come a long ways. And we do have challenges from location to location on practices of insurance plans and so forth, but I do think that it's come a long way. It's important for the patient to ask the right question, right? So if you have an advanced, or a family member has an advanced tumor, it is important to basically ask what trial opportunities and what sequencing opportunities there are. Sometimes, these things don't come up unless you ask, unless you advocate for yourself. And for the most part, they can be sent off now, and plans will cover these things. And for advanced tumors, you remember most of the people the patients, my dear patients that have gained benefit from these early phase trials, went on a trial, right? So when you are when you have advanced disease and you know, based on your input from doctors and from your own research, that the options with standard of care are not as good, then exploring good trials for next generation therapies are very, very important. For instance, in clinic, I treat brain tumors, glioblastoma, okay? I recommend standard of care therapy, but ultimately these things come back, and we know that. And I will be frank with the patient, and I'll tell them that, look, if this comes back, which may be likely, we have to start exploring for trials. And all my long-term survivors are patients that have gotten more aggressive therapy on certain trials. So I guess that is an answer to the access part, right? The therapy part, which is don't be satisfied with standard of care. That's why folks like UT Southwestern, MD Anderson, Texas Tech, Cleveland Clinic, we spend so much time trying to advance that therapeutic frontier, right? Because you see what can happen, you know, when the right patients are matched with the right treatments.
Any questions from the audience? Yes, we have plenty. And are we going to have a microphone or just yell them out? Okay, good.
This is sort of a two-part, but why is there a quote-unquote age limit on the Gardasil vaccination? And why would we not all get these vaccinations if available? Is there some downside to taking these vaccines?
Well, the answer to your first question is, why is there an age limit? It's basically, and you're gonna do the advanced talk here. I'm gonna do the simple. It is that when we vaccinate young immune systems, they are more apt to learn. As we age, our immune systems aren't quite as efficient at learning. Would you agree?
Yeah, I think so.
So that's the age. The second part of your question is very apropos, and the truth is it's cost, and that we know that the benefit of the vaccine isn't for everyone, and there are always risks. Just like we've seen with coronavirus vaccine, there will always be a subset that won't do well on the vaccine. So it's risk-benefit of when you're going to engage the new technology.
So I think those are perfect answers. I'll just add on one additional thought is that it takes time for HPV to cause cancers. It can take years and years. And so the vaccine is very good at preventing the onset of the cancer from its starting in the first place, but it was not designed to actually treat once it's started. So what can happen is a woman could get infected, or a man can get infected with oropharyngeal or whatever, and you see that incidence of the tumor goes up over years and years, over the next 20 years, right? When you vaccinate early, that is before exposure. And that is when your immune system is most able, as Dr. Baker said, to be able to identify and destroy any potential things that are foreign. And in fact, before the tumor developed, there's no cells, there's no tumor cells to fight against. Later on, let's say a woman has already been exposed and there may be pre-malignant cells already there, well then the vaccine becomes less effective. So that's the other reason. This version of the vaccine is not tailored to be able to fight off. It's not a therapeutic vaccine like I was talking about, which is much more complicated. And that's part of the reason.
Is there such a thing as too many vaccines over a lifetime? Because, I mean, this is maybe a really stupid question for a scientist, but does your immune system get kind of worn out and tired of fighting off these things? When you're 100 years old and you've had 120 vaccinations, and also the downside, I'm not sure we've really got to the end of that question. Is there any downside in vaccines? Because the people I know that got the COVID boosters, they seem to do okay with the first two, but a couple of people got really, really, really sick, hospital sick with the booster.
I'll take a stab at that. So I feel you. I mean, I got to say that, all right, so this was my year, all right, last year. Let me think about this, because we're healthcare workers, right? COVID, flu, COVID, DPT, tetanus, flu.
And Shingrix. You need Shingrix.
Oh, I didn't get that one. So it's, and you know, those thoughts went through my mind exactly. Boy, that's a lot of vaccines, and boy, that tetanus shot really hurt. What I will say is that it is, you don't wear out your immune system, I think, because, you know, compared to, I think, the 10 to the 18 to 10 to the 22 combinations, you know, we have plenty of reserve, right? But with each ensuing infection or serious infection, what happens is our immune systems get changed, okay? And as we age, the immune system changes. So the complexity of the immune system, which is your reserve, right, which is what we call the repertoire diversity or the reserve, actually falls over time. So as we age, we do use up our reserve. We make reactions against different things, and age is the number one thing that decreases our immunologic diversity, which is how broad and efficient we can fight off different diseases. So as we age, it turns out that our immune systems are already getting depleted. And that's why when we're older, we need the additional help more. Now, there's a danger to that, and that is the myocarditis, and what you see is real. I had even a colleague get that. And so, you know, we are, you know, sort of the human society as a society, very, very diverse. And we, you know, those orange little epitopes that I talked about, right? They can be used differently in many, many different many people. And sometimes they look like something similar to ours. And so you have to be careful. That's why vaccines need to be tested for a long time. But pertaining to your first question in terms of using up your immune reservoir, I think that's not such a worry, but it does decrease with age. And so that's why I think as we age, it's more important actually to fight off really important threats. And you have to prioritize accordingly.
These are difficult issues because it's risk-reward calculations for each of us, and we're in uncharted territory with respect to these technologies. You know, a lot of the information that we have on adverse effects of drugs develops over years, if not decades, of data collection. And man, you know, we were faced with making some tough choices without having that long-term data with respect to the vaccines and the boosters. Yes, ma'am.
I've just noticed it seems to be that so many friends and loved ones are having pancreatic cancer. And this has not been mentioned at all today. And it's just, again, one of those very, you know, very much dissonance. And any particular findings or anything you can share?
No, you hear a lot of talk about these rarer diseases, lyomosarcs, you know, these rarer cancers becoming more prevalent. But I don't think that I don't think that the scientific community feels like it's maybe any more so. It's just more prevalent at times. Certainly not associated with vaccine, certainly not. You know, there's probably an environmental piece of it. There was some exposure that was significant in those people's lives, but I don't think we're quite sophisticated enough yet to answer that question.
Yeah, there are some hereditary causes that are linked to pancreatic cancer. Those are very rare. A lot of these different types of tumors, like in the brain and in the pancreas, are in these organs that, you know, as human beings, we've developed to be able to sort of not be as inflamed, right? So it keeps the immune system out. And because if you have pancreatitis, for instance, that's a bad thing, right? And if you have infection in the brain, that's called encephalitis. That's terrible. You don't want that. So things like the pancreas, the brain, they have already been they're set up to keep the immune system out. And so they can be more, cancers of those organs can be very deadly just because you don't have that additional boost, like I talked about, to try to control. Whereas, in the skin and melanoma, there's T cells all over the place, and the soldiers are already there to activate, right? So immune therapy, unfortunately, has been very disappointing in pancreatic cancer because you can look at it, it's been tried, you can look at it and the T cells just don't go in. And so there are now a lot of therapies that are in combinations with other types of therapies to try to, break down those barriers. It's like hear about the blood-brain barrier, right? It's kind of like that. There are versions of that in different organs.
I saw several hands, so let's make sure we keep it going. We've got lots of interest in this topic. Yes?
Let's say you have something like just metastatic thyroid cancer, for instance, and you've been to your physician, you've been to your oncologic center, you've been to your Dallas Cancer Center, maybe they send you to MD Anderson somewhere, but you're kind of hitting the wall, you're not making progress. How do you access, or is there an attempt at any level nationally to know what all the labs are doing and to go somewhere to a central database that says, for instance, you two are doing research specifically related to thyroid cancer, metastatic disease, or immunotherapy, or something like that. How do you, as a patient or a family, push through that kind of ceiling, which I'm a retired physician, I know it exists even for physicians in terms of people coming to you and say, where to go? I'm like, and so is there any attempt at that across centers like Cleveland Clinic or Mayo?
The only thing that comes to my mind is clinicaltrials.gov. So any clinical trial has to register with the national government, and that's the website.
So I'll second that. Clinicaltrials.gov is a site, but honestly, as the physicians, all know, that site, unless you have somebody who can really sit down with you with a medical degree, it's pretty unreadable. I've had my own family members that are not medically oriented go to that site, and boy, it kind of sucks, actually. So what I will say is that and you know what, this is a super important access question that you bring up, right? So I'll comment a little bit more about this. It is a dire need in this country, right? Because we're arguing that access to clinical trials is a way to break down, access barriers and increase education. Well, we need the infrastructure to do that. There does not exist a government-wide database that is patient-centric, right? So this has come down to the hard work and dedication of different foundations and institutes. You could potentially think of a way, for instance, to set up a nationwide network and database that's patient-centric for women's cancers, for instance. We've done this, so I'm on the board of a brain cancer one, and that's what we've done. It's called the Brain Tumor Network, and it's a nonprofit. It's free for anybody to come, and it's designed to match up patients with trials. And there's physicians on staff, nurses on staff, and that's what you kind of need, because those barriers are, well, people have been trying to solve that problem for at least 2 decades, right? And it's unfortunately fallen upon, I think, individual nonprofits to do this. Now, that being said, with the proper voices, I think that, there could be a nationwide effort, and it would be fantastic.
Yep, this is really an area where the National Institutes of Health and the federal government can be a leader in putting a network together.
And to be the devil's advocate, I feel like the initiation of it needs to come from the private sector.
Absolutely.
And the setup for it, just like you said, there are different kinds of cancer, different kinds of access. The framework is huge, and then you can solicit out to all the different cancer researchers like you, and related to women's health or cancer, or related to men's cancer, and related to pancreatic, and get all those people an avenue or a access point into that infrastructure to be a part of it. So anyway, I just, as a retired physician or as a physician, even my physician friends don't have access. And I'm like, this is a big link in the chain that is missing and has been. So thank you for saying that.
Other questions? Yes.
Can I just touch on that real quick? I think it really starts at the local level. I work on the ethics committee for an early phase cancer research group, and Mary Kelly Cancer Research is here in Dallas. It's wonderful. They do a lot of first human phase 1 studies. Thing with that, I think it really starts with the oncologist within the community, because they need to be aware, because the patient has to do standard of care first. They have to fail that first before they can go into clinical trial. So if those oncologists are aware of their local network of research institutes, then they can refer their patients to them at that point. And they'd be the best to do that, because you really do have to be local, because when you're in a clinical trial, it's a lot. You're going to the clinic every week, monthly, it's a lot. So they focus a lot on you, which is good, and they're really looking at you, but it takes a lot of time. So I did have a question too. So the self-amplifying messenger RNA, I can see that being a benefit with a disease where you don't produce a protein and you need that protein, so you continue to produce that. But with a vaccine, what would be the benefit in continuing for your body to produce a protein for I don't know how long, and then you have, for example, the virus changes, so you no longer need that protein. What's the benefit, what's the risk of using these self-amplifying mRNAs?
Oh, sure. That's a great question. So these self-amplifying RNAs, or the next generation RNAs, they do go away, actually. They don't stay for more than a week or two, but you need a lot less, and because of the way they're structured, they're circular. They don't have to be stored at ultra cold temperatures, and they can be transported. And the other thing is you can fit a lot more in. And why that is important is because of, I will talk about HIV a little bit, right? So HIV and AIDS was uncontrollable with single agents, but it wasn't until the combination of 3 or more agents when you could actually halt the virus, because it would mutate. Same thing with cancer and coronaviruses. Right now, all the first generation vaccines hit one spot, the spike. And that's why we're getting so much, variants that come out. The self-amplifying RNAs allow a much larger cassette to go in because they're more stable, and you can hit, the ones that are being designed now hit something like 20 spots. So it would be impossible for this thing to mutate out of. So those are some of the benefits. There are other advantages. The RNAs, for instance, now that are being used by Moderna and others, they use these chemical modifications, and the RNA is a little bit difficult to make. These things streamline manufacturing, and there are a lot of other logistical issues that become easier.
Yes.
When do you think the new vaccine will be out that will cover all the 20? And how often will you have to take it?
Well, that's unknown. We're in uncharted territory. These are right now in phase 2s, and there are a number of them. There's a SAM one. I think Moderna's making one. There is probably a half a dozen of these that are making their ways through trials. I would say in the next, the urgency has come down a little bit because thank goodness we're getting out of the pandemic, I think. But I think, these will probably finish up in the next year or so, and you have to make a decision whether you want to do it or not. Some of it is, really dependent on, nobody knows what's going to happen next, right? Or whether there's another one waiting, or whether it's going to be another generation or two before something happens. So, we'll all have to decide as a society, but it's good to at least have them there, so that, they're available. But I would say they'll probably be approved maybe in about a year and a half or so.
I guess I'll hand in the back if there's still one. Maybe not. Okay.
I was just wondering, so when you identify like the epitope, like how that functions with the disease, like how do you share, or do you share that across, like, I can't think of the word, my brain's, but like across different diseases, like for instance, Alzheimer's or cystic fibrosis, like if you've identified that is a way, like how do you, besides reading those journals, like how would you, in my
No, that's a great question. I can tackle that if you want. So, yeah, so that's a great question. Okay, so when a cancer develops, there are certain genes that are very frequently mutated that change, and those happen often in the same places. So they can happen in pancreatic cancer, like P53 is just one example. That happens in lung cancer, it happens in head and neck cancer. And so there are approaches to try to harness the similarities across different types of tumors. There also are personalized ones, which is why individual sequencing is important. You figure out what your tumor looks like. No tumors are identical. Right? There are no identical tumors, but there are similarities between different tumors, between one patient and the other. So it's a combination, and there is, just an enormous amount of effort globally looking at these now, using a mix and match approach, a combination of everything you mentioned, right? The ones that are shared, the ones that are not shared. You've heard about CAR T cells, maybe, or this was in the New York Times, Wall Street Journal about 2 weeks ago. The patients were 10 years disease-free from CAR Ts, which are T cells that have been programmed to hit those particular epitopes. Some of those shared ones can result in long-lasting disease control in single disease types, like in leukemias, but not in others. So it's a big mix and match right now that's happening. And I think progress in general is being made, but a lot of those questions still need to be answered. How much in common do individual drugs need to be? How personalized does it need to be? And it's likely going to be different between different types of cancers.
This is actually a very big topic with patients. They come in and they know these therapies are available, so they want to know what their markers are. Tell me what my genetic markers are. And that is a long conversation and a very hard decision that I think we all have to think real strongly about, because just if you had one of the markers doesn't mean you're going to develop that cancer. And what are you going to do to surveillance, and what's that going to do to your mental state to think, heaven help us, in 15 years I'm going to have pancreatic cancer. I don't think we're quite there yet. Now, if you had a really strong family history and you had reason to do that, I could get on board with that. But for us all to do that and live with the burden of what may or may not happen in your health, that's a much bigger question.
So I would really agree with that, because you want to use information in a way that increases your general well-being, right? And so there are a lot of different tests out there that are marketed to patients, but you want to, in my mind, at least this is how I live, is that you want to selectively utilize the ones that are going to help you and make good decisions. And part of that is, if you get a test, there better be an option to do something about that test. If you get a test and it tells you something that you can't do anything about, then what's the point? Right.
Yes, ma'am.
With Gardasil, how much does it cost, and would our indigent population have any access to it?
It's $5 a shot at the health department, at your local health department. And I spend most of my Saturdays giving shots for free off of grant base, like he was talking about, but it is widely available. The issue of Gardasil being available is not there. It's the issue of people accessing it.
Yes.
I definitely think you're seeing more information about the head and neck cancer issue. For a long time, it was really targeted to women, but I do think some of the health strategies are different now. I'd like to see one that says don't smoke and get Gardasil. Would that?
And try not to vape either.
Yeah.
That's an important point, is that, use the public health data to help drive our policy. And it's an excellent point that's made. It's no longer, tobacco-related cancers. We've got other sources that are important that we have to focus on. And I, from a personal standpoint, I would agree that, in the initial stages, Dr. Baker made the point eloquently about, thinking about my 12-year-old child having sex.
I'm sorry.
No, I have 2 daughters. They're older than 12. Anyway, so I remember that was part of the conversation in the early stages. It really makes parents kind of reluctant. I mean, you put those 2 things together, teenage early sex and a vaccine, you're already, I think, putting the vaccine messaging at a disadvantage. And so I think it's public health policy as well as coming up with a strategy for messaging that makes sense, that doesn't turn people off to these very important life-saving approaches. Yes, ma'am.
About the HPV, my generation that didn't have the HPV. And how long did you say it takes for the virus to?
About 30 years.
About 30 years.
Yeah, but
Is that why about 10 years ago, all these men I know got throat cancer?
it's possible, but I would just like to alter your first sentence. In your generation, which we're not very far apart, we had HPV, we just didn't know it.
I mean, the vaccine.
The vaccine, yes, yes, absolutely. It takes, on average, 30 years from infection to cancer with HPV.
Your doctor swabs you. They can test you for that. It's part of their checkup.
Mm-hmm.
And they should let you know you're HPV positive or not. So.
Yeah. No, I just was thinking, about 10 years ago, I knew a lot of men that were diagnosed with throat cancer. And so you do that.
Well, no, it's an epidemic. I mean, it really is, there was a spike.
In their 20s, so that, how does that correlate with 30 years? When you're, well, so they were in their 50s when they were.
Okay, so I'm gonna scar everybody again, but apparently.
Hey, this is a debate chamber, so let's go.
So apparently the age group from 18 to 26 is who has all the sex in the world. So then you just do the math. So if you have sex when you're 20, then you get cancer when you're 50. That's kind of depressing, isn't it?
Connie, did you have a question?
I did, in a conversation with Dr. Chan early on, he mentioned that this science is, and of course we're focusing on cancer, but this same science is making some amazing progress with leukemias and with multiple sclerosis. And so I thought if you would just address chronic disease a little bit and what some of our newer expectations might be in that area.
No, Connie, that's a great question. So, I focused on cancer a lot today, but I did mention a few other diseases like multiple sclerosis. So multiple sclerosis has now been shown to be directly linked to EBV infection, one of those viruses. And this is quite common, and there's certain strains. It turns out that you can vaccinate against EBV, right? And they've been endemic in certain parts of the world, causing lymphomas in some populations and head and neck cancers in others. And so there's more than one reason. It infects. It's a virus that can span both infectious diseases and neurodegenerative diseases like MS. And if you have a friend or if you have a family member with MS, you know how devastating and completely incurable that is, right? So these are all opportunities for vaccination as we're learning more about this. There are other types of diseases, autoimmune diseases, which is a turning on of the immune system's attack when it shouldn't be on. It's attacking self, right? Remember, self versus non-self. These T cells are, for some reason, they got it in their heads to attack yourself, okay? And so you have to turn them off. One way to turn them off is if you have these vaccines, these epitopes, and you don't put in the immunostimulatory portion, you just provide the epitope, it can actually have a paradoxic effect of turning off the immune system. So there's now going to be a whole generation of vaccines, once we know what the epitopes are for things like rheumatoid arthritis, for things like scleroderma, lupus, right, which really affect a lot of folks much more heavily in women, of course, because there's a sex predisposition there, that these potentially are exciting ways to try to control the immune system. Right now, all we have are blunt tool instruments like steroids, for instance, that cause a lot of side effects. And so we'd like to move beyond that with some of these vaccines. And that is really at the state of the art right now. For very, very severe multiple sclerosis that is life-threatening, we even have bone marrow transplant. These were big breakthroughs. Now, this is not for everybody. This is a very, very tough therapy. As some of you may know, folks with leukemia unfortunately have to get bone marrow transplantation. It's where you get a lot of chemo, you wipe out your immune system, and then you basically get a transplant back. That's been shown to actually be able to cure multiple sclerosis in some cases. But it's, we don't want to go that route if we don't have to, and some form of immunomodulation may be a little bit better. And that's where a lot of research is for those types of non-cancer diseases.
Are those
Okay.
new next generation treatments, do they have less side effects? Are they less, do they ravage the body a little less than the early bombardments of chemo when you're doing standard procedures?
No, absolutely. So these vaccines have relatively very few effects. For anybody that's gone through chemo or has a friend that's gone through chemo, it's awful, right? Or radiation, awful. So this is much, much, much easier, right? You may have some rash, you may have some fever for the most part. So they are designed not to be a blunt instrument, right? But even the first generation immunotherapies like hormonal treatments, IL-2, for instance, really trick your body into having severe fever, right? Severe infection, and people get really, really sick. And so these don't have those problems.
We'll have one more question. And, well, maybe two more questions. Two more questions. Yes?
Talking about neurodegenerative diseases, does SMA fall into any of this? Is that a spinal muscular atrophy, something like that comes on and progresses? Is that a target for this kind of therapy? Is there something that you're familiar with that targets this disease?
Yeah, there are some target therapies, not immunotherapies for that. There's some gene therapies. There's hereditary forms of that, as well as for Lou Gehrig's disease as well, which is similar. But yeah, not as much there. This field is just getting started in the last year or so.
Please.
In the future, would cancer vaccines potentially replace chemotherapy, radiation, surgery, or is it just another tool?
I think probably it will be another tool. Just for cost perspective, for like he was saying, only 50% responded to the immunotherapy. Maybe that other 50% will respond to the traditional therapy.
That being said, I will say there is nothing easier than preventing the disease in the first place, right? If there's a Gardasil available and you can get it for $5 at the CVS and it will prevent all sorts of hell from breaking loose down the road, it's not a bad idea.
Great. Thank you. Dr. McMahon, Dr. Baker, Dr. Chan, thank you so much. They will be here at the front of the room if you have additional questions. And we'd love for you to support us at the Laura W. Bush Institute so we can have more of these symposiums in the future. Have a great afternoon. Thank you for coming.